In this mini lecture, we will learn about the final set of reactions of alkenes and alkynes, and these involve oxidation and reduction reactions. We've seen that the carbon-carbon double bond is an excellent nucleophile. It's also an electron-rich portion of a molecule due to the existence of the pi bond. And when we react that carbon-carbon double bond with a hydrogen molecule in the presence of a catalyst, we can add a pair of hydrogen atoms across the carbon-carbon double bond. We can also add a pair of OH groups across the carbon-carbon double bond by using a reagent called osmium tetroxide. Both of these reagents add syn across the carbon-carbon double bond. If we remember back to another reaction that did a syn addition, the addition of BH3 across the carbon-carbon double bond, we saw that the reason for a syn addition is that the reagent basically sits down on the carbon-carbon double bond. Since the reagent sits down at the same time onto both carbons of our carbon-carbon double bond, we end up getting an overall syn addition to the carbon-carbon double bond. Let's look first at the hydrogenation reaction. What's observed is that you can mix an alkene with hydrogen gas, and you can basically get no reaction for a very, very long period of time, days, weeks, years, centuries. And the reason for that is that the mechanism by which the hydrogen would add across the carbon-carbon double bond requires a catalyst. And the best kind of catalysts for this reaction end up being noble metals: palladium metal, palladium on carbon, platinum metal, or nickel metal. There also are some homogeneous catalysts. These are catalysts that are soluble in the reaction medium, derived from metals like rhodium and organic ligands, triphenylphosphine. This reaction is highly exothermic. It's downhill, and yet without the existence of a catalyst being present, the reaction does not occur. Even a sliver of palladium could cause the reaction to occur explosively, leading to conversion of our alkene to an alkane. When hydrogen interacts with the catalyst, and let's view this catalyst here as being palladium, the hydrogen-hydrogen bond breaks, giving rise to a pair of surface-bound hydrogen atoms. Those surface-bound hydrogen atoms can interact with our alkene molecule and attach one of the hydrogens to one end of the carbon-carbon double bond. The remaining carbon atom remains attached to the surface of the palladium metal. In the final step now, the hydrogen associates itself with the palladium-bound carbon, leading to overall syn addition of hydrogen across the carbon-carbon double bond and regeneration of our palladium catalyst. So this is a catalytic cycle. We only need trace amounts of palladium for this entire reaction to occur. Here's an example of how the hydrogenation reaction is actually extremely useful. It allows us to take the carbon-carbon double bond of this alkene and add a pair of hydrogens to it, this one and this one. The two hydrogens are added syn to one another. Our starting material is an achiral molecule. By using a catalyst that has chiral centers in it, we can actually add hydrogen only to the bottom face. And as a result, we get one enantiomer of our product, which ends up being S-dopa, the drug used in the treatment of Parkinson's disease. So here's an example of an extremely valuable product that's made by adding hydrogen to an achiral molecule, leading to a chiral single enantiomer of our product alkene. Now, hydrogenations are also used to convert vegetable oil to margarine, which is called hydrogenated soybean oil. Not good for your arteries. And so this is prevalent quite commonly in industrial processes. In the hydrogenation of alkynes, we have a carbon-carbon triple bond that can interact with hydrogen, and it can add once or twice. With regular hydrogen and platinum, or hydrogen and palladium, we add not just one, but two equivalents of hydrogen across the triple bond. And so we convert the carbon-carbon triple bond into a carbon-carbon double bond. In order to stop at the carbon-carbon double bond, we need to use some special catalysts and special reaction systems. Hydrogen and Lindlar's catalyst allows us to add hydrogen syn across the carbon-carbon double bond, and it gives us an alkene instead of going all the way to form the alkane. This is extremely useful because now we have a convenient way to make a cis-alkene. Now, Lindlar's catalyst is a very complicated reaction mixture, and it's quite amazing that it was discovered. It's a mixture of palladium, I believe calcium carbonate, a molecule called quinoline. Basically, it's a poisoned palladium catalyst that allows the reaction to stop at just one addition of hydrogen. We can also get the anti-addition of hydrogen across a carbon-carbon double bond by using lithium metal and ammonia. Lithium metal is a good source of an electron. Ammonia is a good source of a proton. Even though NH2- is an extremely strong base. Well, electrons and protons together, if we had two lithiums and two ammonias, we would effectively have the elements of hydrogen. And so this reaction adds hydrogen without ever actually having molecular hydrogen, H2, in the reaction system. And this is an anti-addition. Let's look now at the dihydroxylation reaction. This has the molecule OSO4. It's called osmium tetroxide. It's a really powerful oxidizing agent. It reacts quite conveniently with a carbon-carbon double bond. And as it is a high oxidation state metal, osmium, which is below iron in the periodic table, it's very easy to reduce the osmium's oxidation state. In the starting structure, it's actually an oxidation state of 8. When it adds to the carbon-carbon double bond, the oxidation state gets reduced to 6. So the osmium gets reduced at the same time that the carbon-carbon double bond has 2 more oxygens added to it. So the carbon-carbon double bond gets oxidized. Since osmium is a stubby reagent, the 2 oxygens hang together, attached to the osmium. They're forced to add on the same face of the carbon-carbon double bond, leading to syn addition. This cyclic intermediate reacts with a water molecule to open up the 5-membered ring containing osmium and generate our product, which is a dialcohol, or a diol, all meaning the ending for the alcohol functional group. And we get a molecule of osmium-6. Now, osmium-6, the osmium in general is quite expensive, and so this reaction can be made catalytic by having trace amounts of the osmium starting material and hydrogen peroxide, which can reoxidize the osmium-6 back up to the osmium-8, forming a catalytic cycle. So this is an excellent way to take an alkene and convert it to a diol. Let's look at a few examples. In this first one, hydrogen is a reagent that adds syn across a carbon-carbon double bond. And so our 2 hydrogens are going to end up on the same face of the molecule. We could draw the 2 hydrogens both on wedges or both on hashes. In this particular case, the molecule is the same whether we draw the 2 hydrogens on wedges or on hashes. And so this is the only product of the reaction. It is a achiral molecule. It's a meso compound. Has two chiral centers, but is overall achiral. Now in the bottom example, we have a carbon-carbon double bond, and we have osmium tetroxide. And the osmium tetroxide adds a pair of OHs to the same face of the carbon-carbon double bond. Here, the two oxygens could have ended up both up on wedges. Oops. Both OHs on wedges. Or both OHs could have ended up on hashes. These two molecules are mirror images of one another, and so they are enantiomers. Reaction conditions have also been found where osmium tetroxide can be made to be selective, so we can favor one of the two diol products in this reaction. And Barry Sharpless obtained the Nobel Prize many years ago for discovering that particular reaction. Now, if we look at a series of alkenes with 4 carbons in their structure, 1 butene, and cis and trans 2 butene, all 3 of these molecules form exactly the same product, butane, when they react with hydrogen. So the energy of the product is the same in all 3 of these reactions. The first reaction releases negative 127 kilojoules. The second one releases negative 116. The third one, negative 120. So the first reaction releases the most heat. And the middle one releases the least heat. Let's take a look at the implications of this. So if we start off with an alkene, and it reacts with hydrogen to make an alkane, and then we have another alkene that reacts with hydrogen to form the same alkane, the amount of heat released in the reaction is a measure of how stable our starting material was. If our starting material was high in energy, then this reaction is going to be very exothermic. If our starting alkene is low in energy, then the amount of heat that's released is very little, and it's less exothermic. So as we look at those alkenes that form in this reaction, the alkene that releases the most heat is the 1-butene. The alkene that releases the least heat is the trans 2-butene, with the cis 2-butene somewhat higher in energy than the trans 2-butene. And we can recognize what this tells us is that 1-butene is a less stable alkene. Because it's a high energy alkene, it reacts with hydrogen to form a more stable alkane, and in the process releases a lot of heat. It's very exothermic. Trans 2-butene would release the least amount of heat, and as a result, it's the more stable, or the most stable alkene, releases very little heat, and goes on to form the same product, butane. So from the heat released during hydrogenation, also called the heat of hydrogenation, we can get a measure of the stability of the alkene that we started with. So based upon this, we say that trans alkenes are more stable than cis alkenes, and that cis alkenes are more stable than alkenes that are at the end of the carbon chain. So we can understand the cis versus trans. If this is the pair of carbon atoms of our alkene, the cis alkene actually places the pair of methyl groups very close together. and there's steric strain between them. In the case of the trans 2-butene, those methyl groups are very far apart. And so we have a much more stable alkene in the form of the trans alkene than we do of our cis alkene. In general, the higher the degree of substitution our alkene has, the more stable it is. And the origin of that is that these methyl groups are excellent electron donors. And so with more carbon atoms attached to the alkene, the carbon-carbon double bond becomes a more electron-rich, a more stable carbon-carbon double bond. Let's look at dienes. This molecule has two carbon-carbon double bonds separated by an sp3 hybridized carbon atom. As a result, the two carbon-carbon double bonds are not conjugated with one another. In the bottom example, the two carbon-carbon double bonds are directly attached to one another. The sp2 atoms of the two alkenes are directly bonded together. The first molecule releases much more heat than the bottom one. It's more exothermic. And as a result, the alkene that we start with is the least stable. It's the highest in energy, and it releases the most energy to form the product. And notice that with both alkenes, both dienes, the product is identical. So we can derive information from this by looking at molecular orbital theory, but the origin of it is that the two carbon-carbon double bonds, when they're in conjugation, allow us to have molecular orbitals which end up being lower in energy than isolated pi bonds. Let's look at the final kind of reaction that we have with alkenes and alkynes, and that's called the oxidative cleavage reaction. The carbon-carbon double bond of an alkene can react with ozone and a reducing agent, very often zinc metal and acetic acid, to cleave what was once the carbon-carbon double bond into a pair of carbonyl groups. If the starting material had a hydrogen on it, then our product is going to have a hydrogen on it, and an aldehyde would be our product. We don't need to worry about the mechanism of this reaction, and there is no stereochemistry or regiochemistry. Another reagent that accomplishes the same transformation is permanganate. And you'll look in your book and they'll have some conditions that will say cold dilute permanganate or cold basic permanganate or cold acidic permanganate. I want to lump all of those reactions into one general category, which is that permanganate also cleaves the carbon-carbon double bond. In some cases we can isolate a diol as the product, but by and large we get cleavage of the carbon-carbon double bond to give us a pair of carbonyl groups. And so the reaction could occur like we see with osmium tetroxide, but more often than not it's a messy reaction and we get cleavage of the carbon-carbon double bond. Now the origin of the word oxidative cleavage is that the cleavage occurs because we actually break the carbon-carbon double bond. And in the process, the two carbons that were part of the carbon-carbon double bond get oxidized to carbonyl groups. Well, the final reaction is not a reaction of an alkene at all. It's a reaction of a diol, but it's very similar to the reactions in this group. If we have a diol where the two OH groups are on adjacent carbon atoms, it can react with a reagent called HiO4, and give rise to a pair of carbonyl groups, resulting from cleavage of the carbon-carbon single bond. The two carbonyl groups, the two carbonyl groups have an oxygen that derives from the HiO4. Now in the case of permanganate, if one of our carbons had a hydrogen on it, then our product is actually a carboxylic acid. And the reason for that will become clear in a later slide. In the ozonolysis reaction, the alkene can react with a molecule of ozone to form a 5-membered ring
intermediate, which rearranges to give a different kind of 5-membered ring intermediate, which on reaction with zinc and acid gives us a pair of carbonyl groups. So this reaction is what happens with rubber-based products when they're exposed to air that has a high level of ozone, and is the reason why latex gloves won't survive very long when we have them in Los Angeles compared to areas that have much lower ozone layer levels. And so this is a reaction that simply cleaves the carbon-carbon double bond by inserting some oxygens into the structure. The permanganate reaction occurs by a very similar process to the ozonolysis and the osmium tetroxide reaction. Manganese tetroxide sits down on the carbon-carbon double bond to make a 5-membered ring intermediate, and then the carbon-carbon bond gets cleaved to give us a pair of carbonyl groups. If one of these carbons had a hydrogen on it, in other words, our product was an aldehyde, then permanganate can actually over-oxidize that aldehyde to a carboxylic acid. Aldehydes are fairly electron-rich molecules, and in the presence of an oxidizing agent like permanganate, they can get oxidized to the carboxylic acid. Finally, the periodic acid reaction is nearly identical to all the others. We start off with a diol that reacts with HiO4. We form this cyclic intermediate, and in the process we cleave the carbon-carbon single bond to give us a pair of carbon-oxygen double bonds. And this occurs without over-oxidizing one of the carbon atoms. So if one of these carbons had a hydrogen on it, then we would have an aldehyde as the product. Let's look at a couple of examples. In example number 1, we have a hydrogen on one of the carbon atoms. This reaction, the ozonolysis, cleaves carbon-carbon double bonds. Note that our first reagent is ozone, but our second one is one that we haven't seen before. This is dimethyl sulfide. It has a garlic odor, and it too, just like zinc and acid, can serve as a reducing agent. So the same reaction as we saw before. The reaction cleaves the carbon-carbon double bond and replaces the carbon-carbon double bond with a pair of carbonyl groups. And so this is now a pair of separate molecules, 2 different molecules being obtained from the single molecule of our starting material. If we tried using this reagent on a cyclic alkene, where the alkene was contained in a ring, for example cyclohexene, then the 2 ends of the molecule would still be tethered to one another, and we could get a molecule with the carbonyl groups contained within the same molecule. Let's look at another set of conditions, permanganate. Now, one of the carbons of our alkene has a hydrogen on it. And so as this carbon gets cleaved, we can initially get, I'm going to miss a carbon atom here if I'm not careful. Good to number your atoms. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. We're going to initially have an aldehyde form at carbon number 6, but then that aldehyde is going to quickly get over-oxidized to give us a carboxylic acid. The top part of our molecule is going to get cleaved to give us a ketone. So in this case, the 2 carbonyl groups that form are actually contained within the same molecule. Look at one final example here. In our first problem on this page, our 2 OH groups are cis to one another, and in our second example, the 2 OH groups are trans to one another. In this reaction, we must form a cyclic intermediate. And in order for that to happen, the two OH groups must actually be able to be on the same face of the ring. And so for the bottom example, no reaction occurs. But in the top reaction, we can get cleavage of the carbon-carbon single bond and giving rise to a carbonyl group on the top carbon, number 1, and a carbonyl group on number 6. The bottom carbon having a hydrogen on it stays as an aldehyde. The top carbon having a pair of carbons on it remains as a ketone. And so this is the overall product of this step, which is identical to the product in the previous problem. Finally, alkynes can also be cleaved by some of the same reagents that alkenes can. Ozone and permanganate will cleave the carbon-carbon triple bond. But when the carbon-carbon triple bond cleaves, we get a pair of carboxylic acids. And so this reaction simply breaks the triple bond and gives us a pair of carboxylic acids.